Hi, I'm Rohan Ramnath, and on this slide are my co authors from LinkedIn. In the talk, we describe internet marketplaces and how to optimize them using linear programming methods. We describe why this is a hard problem to solve at scale and propose Duolip, LinkedIn's open source LP solver to accurately solve massive scale matching problems. Our method achieves an order of magnitude improvement over the state of the art. We start by motivating the problem, then represent it using an LP formulation. Finally, we get into the details of our solver along with the algorithmic improvements to the projection step. Let's jump into the problem statement. Most products care not about just one but multiple business objectives. Some prominent examples are email and notifications. They form a key component of every company's growth strategy today. In deciding which emails or notifications to send, we care about the engagement generated while being mindful of the volume of such emails sent. Newsfeed and search ranking are core applications for social networks like Instagram, Twitter, and LinkedIn. In social networks, these can be thought of as edge recommendation systems. In such systems, two objectives are of key interest: the number of edges formed and the engagements those edges then generate. E-commerce giants like Amazon, Walmart, and Target are often balancing overall revenue, in-house revenue, and member satisfaction or retention. Finally, there are the various gig economy platforms like Uber and Airbnb, where there are multiple sides to their marketplace. For instance, Uber Eats has customers, drivers, and restaurants, and each side have got their own separate objectives. Today we will discuss how to efficiently strike a desired balance between different business objectives and why we believe large-scale linear programming solvers provide a step function improvement in our ability to do so. Many other applications at LinkedIn and outside have a very similar form. They care about multiple critical objectives, which are often conflicting among themselves. Another important example of this at play is our paid job recommendations product, where the system is trying to balance the total number of confirmed hires on the platform as well as the revenue coming from our premier jobs. We call these applications, which share the key property of having a very small number of constraints, multi-objective optimization problems. Each such constraint requires considering all instances or a significant portion of all instances. Move formulations are popular for optimizing an entire page, especially home pages like in Netflix and Amazon, which direct traffic towards various parts of the platform and hence drive associated business metrics. Now, let's consider a different class of problems. In the people you may know matching problem, we want to recommend people that you either want to know or might already know but are not connected on the platform. We would like to do this in a way to ensure that no member is overwhelmed by receiving too many invitations. While the structure of the problem is similar to the move problems, there is one key difference. The number of constraints are much larger. Each item can potentially have a constraint. We call these matching problems since we are pairing items with members. PYMK is a special case where a member can both be an item as well as a member. The job recommendation and ad recommendation are two other problems where the job is the item and members are matched with jobs, and in the ad recommendation problem, the ads are the items and members are matched with ads. In the marketplace matching problem, there is a possible constraint associated with each stakeholder on at least one side of the marketplace. This typically means hundreds of thousands to millions of constraints. The numbers here are just to help you appreciate the size of the marketplace that we deal with on a daily basis. So matching in marketplaces is the second key problem class where the number of constraints is much larger than Mu problems. Many companies providing services in the gig economy are solving such matching problems, like drivers to riders on Uber or hosts to visitors on Airbnb. We now look into how we should translate these business problems into a linear programming formulation. Let's start with the Mu problem. The variable of interest for us is x sub ij. Let x be the probability of sending an email j to a member I. There are two utility models, P and Q, where P is the probability of getting sessions from member I if email j is sent, and Q is the probability of getting a complaint from member I if email j is sent. So now our objective, which is the downstream sessions, can be represented as the expected number of sessions, which is nothing but the sum over ij, xij times pij, and the expected number of complaints, which is sum over ij, xij times qij, can be bounded by a constant b. You notice that this problem formulation has just one global constraint, which is the expected number of complaints should remain under the specified bound. We also see a constraint in blue called the non-coupling constraint. The entire purpose of this constraint is to ensure that our variable of interest remains a probability. In terms of scale of this problem, we have 100 million members and about 10 email campaigns running every day. So the total number of variables, decision variables we have are about 1 billion decision variables. In a very similar way, we can also transition the matching problem as an LP. For sake of time, I only want to highlight the differences. The supervised ML models here predict the invitation and acceptance probability. For example, model P represents the probability that member I will send an invitation to member J, and the model Q represents the probability that member J will accept member I's invite. The variable of interest X now represents the probability of showing member I to member J. Note that since this is a ranking problem, we must show at least one recommended member to every viewer, which gives us the blue simplex constraint. Looking at the scale of this problem, as before we have 100 million members, but we now consider 10,000 member groups or cohorts that we want to set constraints on. And this gives us a total of 1 trillion decision variables. I want to highlight that unlike the Mu problem, here we have a large set of constraints. Although I described the Mu and the matching formulations differently, they can be unified into a general LP formulation. In both cases, we have linear objectives and linear constraints. The linear constraints encoded as the matrix AX less than or equal to B, where the matrix A unifies both the global constraints and the per member constraints. The non-coupling constraints written in blue are different in both cases, but once you understand how we solve the problem, it's easy to see that we can support a host of different non-coupling constraints depending on the business needs. To give you a sense of our evolution of scale, back in 2015, we used a subsampled version of our marketplace with operator splitting methods to solve these LP formulations. As the size of our marketplace grew, the subsampling and approximations reduced the quality of our solution. In 2019, when the splitting conic solver was published by a research group at Stanford, we removed all of the approximations in the marketplace and scaled up the solver to about 20 million variables. With this, we saw considerable improvement in product metrics. And we set ourselves the goal of solving an LP formulation with at least 1 trillion decision variables with the focus on an accurate solution. And that was our goal for Dualip. Dualip is our open source linear programming solver that can solve extreme scale matching problems and can support a wide variety of projection operators. To give you a high-level overview of our approach, we start with the primal formulation, convert that primal into its dual form, add a smoothing parameter or a regularizer to make the dual function smooth. The dual now is represented in terms of an inner minimizer and an outer maximization loop. We solve that inner minimizer using a projection operator and use the solution of the projection to compute the gradient of the dual function in a closed form. We now have access to the gradient and can use a smooth gradient-based descent function to solve the optimization problem. We implement all of the components described in the previous slide and then profile the solver for computational bottlenecks. We run the solver on a 100-node cluster, and all variables with the subscript I are computed in parallel on node I. The chart shows the distribution of time spent on a single iteration of the solver. And it is easy to see that despite the parallelization, almost 3/4 of the time is spent in computing the projection. So to make the solver faster, we decided to investigate a faster projection method. Let us first start with what is a projection. Projections are essentially constraints on the decision variable. In the email volume optimization example, the projection enforced that the decision variable was a probability. In the PYMK matching case, the projection enforced that every member had at least one recommendation. We analyze some common problems in marketplaces and represent them as LPs, where each column shows one component of the formulation: the objective, the coupling constraint, projection type, number of coupling constraints, and the scale of the decision variable. You might notice that the scale of the problem varies anywhere between 10 billion to 1 quintillion variables. The importance of the slide is to highlight the variety of projection operators. We will now talk about the business consequences of choosing each one. The first constraint enforces the model score to behave like a probability. This is useful in applications like email volume optimization, where send decisions are based on the model score. The next type of constraint is used in ranking formulations when we need to return the top delta items. We saw a special case of this with delta equals 1 in the PYMK matching example, where we used a simplex constraint. Some marketplaces have a notion of budget. Example, ads and paid jobs typically have a daily monetary budget that they don't want the platform to exceed. In ranking formulations that honor such budget requirements, we use this third kind of constraint. When we assemble different types of content onto a page or news feed, each position on the feed can correspond to a different reward. We encode such constraints using a bipartite graph. And lastly, when the different items are sponsored items that are priced using an auction, the position at which they finally finish not only changes the total reward, but also changes the cost. Such constraints are encoded using a directed acyclic graph. To understand the intuition behind our approach, it is important to think in terms of the geometry of the projection operations. Every operator that I spoke about can be represented as a polytope, and projection is the process of finding the closest point on this polytope. We have looked at internet marketplaces, and one key property of internet marketplaces is the two sides of the marketplace are typically skewed. Either demand constraints or supply constraints make one side orders of magnitude smaller than the other side. The crux of our paper can now be summarized using Sard's theorem. Results from theory show that in such skewed marketplaces, the projection operation prefers vertex solutions, or the solution is on the vertex of the polytope. We show in our paper that in most cases, over 99% of our decision variables will lie on the vertex of the polytope. Now, our goal was to use this very useful, unique insight to modify our projection algorithm and therefore speed up the entire solver. To understand our vertex-oriented projection operator, let us use the definition of a chorale. A chorale is a convex hull of a subset of vertices of the polytope that contains the projection. For each of the special polytopes discussed before, we have efficient algorithms to incrementally generate the next closest chorale. We do this in increasing order of chorale dimension. We also designed an efficient algorithm to check optimality of a given chorale. Our algorithm then is to simply start from the smallest coral, that is a vertex, and check for optimality. If not optimal, we check the next closest coral until we find one that is optimal. Now, because of Sard's theorem, we end up finding our projection in the first coral in over 99% of the cases. To demonstrate the speed up in action, we compare our fast simplex method to the simplex method from Ducci et al. On a large dataset in different configurations of nodes. This shows a 6 to 8x speed up in the overall projection operator simply by using this new vertex projection method. Along with the algorithmic improvements to the projection step, we also have improvements to the overall optimizer, as well as novel algorithms to adaptively tune the smoothing parameter. This tuning allows us to trade off the speed of convergence with the quality of the solution. All of these improvements are available in our open source version of the solver. We will now understand the consequences of these improvements on two datasets, a LinkedIn job recommendation dataset and a publicly available movie lens dataset. We compare our results to Eclipse, a solver published in ICML 2020. Let us start by comparing the quality of the solution. In production setups, you often cannot run a solver until convergence. There is a fixed time budget. That is, after a number of iterations of a solver, we evaluate the quality of the solution. In the job matching dataset, Eclipse recovers 3.5% of the fully converged solution after 50 iterations, but Duolib recovers 87.7%. Similarly, after 500 iterations, Eclipse is at 45%, but Duolib is at 98%. This shows that Duolib converges much faster than available alternatives, thereby impacting production setups significantly. The second metric of interest is the scale of the solver. Duolib is not just 20 times faster, but it can solve problems almost 10 times larger and supports 5 times more projection operators than any other alternative solution. It has been used internally to solve problems with 100 trillion variables. This has also unlocked a lot of new marketplace applications that simply could not be solved by previous solvers. Duolib is entirely open source, and we invite contributors and adopters to try our solver on interesting new applications. We would love to hear from you on your experience using it. Please reach out to us on GitHub or LinkedIn with questions, comments, or suggestions. Thank you.